So today we will finish our discussion on phase conjugation, which we started discussing in the last class. So let's recall that what I showed you is if you had a medium possessing a finite chi3 and you send two beams in exactly opposite directions, E1 and E2 waves, and then you send another wave E3 in this some other direction, then there is nonlinear polarization generated in the medium which can generate a wave going in the reverse direction to E3. The space dependence of E4 is exactly a phase conjugate of the phase dependence of E3. So that E4 is called a phase conjugate wave, and this process in which I use the chi3 nonlinearity to generate a phase conjugate wave is called phase conjugation here. Now there are other techniques to develop to generate phase conjugated waves, but this is one interesting technique. So let's try to find out what is the condition under which I will generate E4 and what kind of amplitudes can I get for E4. So what we need to do is look at the wave equation satisfied by E4. We should know the nonlinear polarization generated for the E4 electric field and substitute in the wave equation. So the total nonlinear polarization is given by epsilon 0 chi3 1 by 8 of say E1 exponential I k dot r minus omega t. I am assuming all fields to have the same frequency, plus E complex conjugate plus E2 e to the power I minus k dot r minus omega t plus complex conjugate plus E3 exponential I kz minus omega t plus complex conjugate. So this is the direction. Please note that I showed you there is nonlinear polarization that will try to generate a wave in the reverse direction. So I also add another electric field which is minus kz minus omega t plus complex conjugate, whole cube. This is the wave which is going in this direction. The second term is the wave going in the reverse direction, exactly opposite to E1. E3 is the wave which is coming in some direction which I call as Z direction, and E4 is the phase conjugated wave. Yesterday I showed you that the presence of these three terms generates a nonlinear polarization at the frequency omega, and that polarization will try to generate a wave in the direction of exactly opposite to E3. So assuming that such a wave can get generated, I have added that also into this total electric field expression. So from here what I need to get is an expression for nonlinear polarization at E3 corresponding to E3 and corresponding to E4 fields. That is, what is the nonlinear polarization that will generate the wave going along the E3 direction, and what will be the nonlinear polarization corresponding to the E4 electric field direction. So now if you take a cube of this, for example, if I want to calculate the nonlinear polarization corresponding to the fourth wave, this is equal to epsilon 0 chi3 1 by 8. So if I multiply this first term, this term, and the complex conjugate of this term, I get the term corresponding to the exponential I minus kz minus omega t. So if I multiply this term, and the complex conjugate of this term, so I will have E1, E2, E3 star into exponential minus I kz minus omega, minus I kz plus omega t plus complex conjugate. What will be the nonlinear polarization at for the wave corresponding to E3? So that will be obtained by multiplying this and complex conjugate of the E4 term, because the complex conjugate of this will have plus ikz, and so I will have essentially the nonlinear polarization corresponding to the third term is actually epsilon 0 chi3 1 by 8 of, again, oh, there will be a factor of 6 here, sorry, I missed a factor of 6 here. There's a factor of 6 here in the cube. So 6 times E1, E2, E4 star exponential I kz minus omega t plus complex conjugate. Please note that this nonlinear polarization gets generated by the mixing of E1, E2 and E3. This nonlinear polarization gets generated by the mixing of E1, E2 and E4. So this nonlinear polarization will be responsible for the generation of the E4 wave, and this nonlinear polarization will be responsible for modification of the propagation of the E3 wave. If this nonlinear polarization does not exist, E3 wave would have just gone straight and no E4 would have been generated. But because of the nonlinear polarization, I will generate an E4 wave because of this polarization, and because of this nonlinear polarization, the E3 wave would also get modified correspondingly. So E3 and E4 gets coupled through interaction with these fields E1 and E2. So how do I write an equation for example, this electric field of the E4 term? So remember, we had this equation del square, let me call this, let me call E4 as the electric field. You see, E4 is the amplitude of the electric field of this wave, but let me call total electric field, which contains the space and time dependence, minus mu 0 epsilon of omega del square by del t square of E4 is equal to mu naught del square by del t square of P nonlinear corresponding to E4. We had used the similar equation in second harmonic generation. We had used the similar equation in parametric down conversion. So it's the electric field of the wave coming towards away from the medium. This particular electric field wave will satisfy, the total electric field will satisfy this equation, where E4 is 1 by 2 amplitude exponential minus I kz plus omega t plus complex conjugate. E4 is a wave going in the minus z direction. E3 is a wave going in the plus z direction. So my problem is now to substitute this on the left hand side and substitute this on the right hand side, neglect second differential of E4 with respect to z, exactly like I did for second harmonic, then use the relationship between k and epsilon omega and simplify. The procedure is exactly identical to what we had done for the three-wave mixing. So I substitute E4, this expression for E4 on the left hand side. I substitute this expression for P nonlinear corresponding to the electric field E4 on the right hand side. Neglect second differential of E4 with respect to Z. Use an equation connecting K and epsilon and omega and simplify the equation. So I leave the substitution to you, but as you can already see, the second differential I neglect. The second differential with respect to Z actually gives me two terms. One of them will cancel off with this term and one coming from here. So what I will be left with is the following. So I'll get minus 2I k dE4 by dz is equal to mu naught minus omega square into 3 by 2 epsilon 0 chi 3 E1 E2 E3 star. I leave the substitution to you. It's exactly the same procedure as we had done before. E4 only depends on Z. So del square has only Z differential. So there will be second differential of this with respect to Z, which is neglected. Second differential of this with respect to Z, which will cancel with this term. And then a product of first differential of this and first differential of this, which is actually coming here. And on the right hand side, it is simply a time differential of this term here. So what I'm essentially doing is substituting the first term here, from here and equating on both sides. So if I simplify this equation, so let me simplify this equation. As you can see here, there is no phase mismatch term. If the z dependence of nonlinear polarization and the z dependence of the electromagnetic wave were different, I would have got an extra exponential minus I something here. But because both of them are exponential minus ikz, this is also exponential minus ikz polarization, this is also exponential minus ikz, so there is no phase mismatch term. So I can simplify this and I get dE4 by dz is equal to minus I omega square by c square. So 2k into 3 by 2 chi 3 E1, E2, E3 star. Okay, so there's minus sign, plus, so I got a minus omega mu 0 epsilon 0 is 1 by c square, so omega square by c square, and then a 2k. Okay, so this is equal to minus I omega square by c square. K is omega by c into refractive index into 3 by 4 chi 3 E1, E2, E3 star, which is minus I omega 3 omega by 4 Cn chi 3 E1, E2, E3 star. So let me call this as minus I kappa E3 star, where kappa is equal to 3 omega by 4 Cn chi 3 E1, E2. Okay, so kappa is what is called as the coupling coefficient. It's coupling E4 to E3. The rate of change of E4 depends on E3 through this term kappa. So if chi 3 is neglected, if the powers are very small, if E1 and E2 are very small, then this right hand side is very small and E4 doesn't get generated essentially. So that's a linear situation, almost linear situation. So the coupling depends on the intensity of the light corresponding to the two waves which are going in opposite directions. The stronger the electric fields are, the stronger is the coupling between E3 and E4. Now, you can also derive the similar equation for E3 and you will get the following equation. dE3 by dz is equal to I kappa E4 star. Okay, so I use the same procedure. I use an equation for, instead of E4 equation, I have an E3 equation. I have a nonlinear polarization at the corresponding to the electric field E3. Substitute, simplify. So let me write both the equations here. So dE4 by dz is equal to minus I kappa E3 star. Two equations which actually couple E3 and E4, and the coupling coefficient contains the electric fields E1 and E2. So if I assume that E1 and E2 are constants, that is, I neglect the depletion of electric fields at the first and second frequencies, the E1 and E2 waves, then I can assume kappa to be a constant, and I can very quickly integrate this equation. So this is d square E4 by dz square is equal to minus I kappa dE3 star by dz, which is equal to minus I kappa into minus I kappa E4, which is equal to minus kappa square E4. Let me write this as star, okay, because kappa contains electric fields E1 and E2, which could have some phases in them. So in general, I can assume kappa to be a complex because E1 and E2 can have phase terms. So when I substitute for dE3 star by dz, I take a complex conjugate of this, which is minus I kappa star into E4. So this is mod kappa square. What is solution? E4 of z is equal to A cos mod kappa z plus B I can substitute this into this second equation and get the solution for E3 star. So, let me write in a separate paper. So, E3 star of Z will be I by kappa into dE4 by dz, which is equal to I by kappa into mod kappa minus A sin mod kappa z plus B cos mod kappa z. I've just differentiated this E4 and substituted here. So that's E3 star of z. Now let me try to find out the boundary conditions. I need to calculate the constants A and B. So here is E1, here is E2, here is E3 coming from here, and E4 is coming from here. This is Z is equal to 0, this is Z is equal to L. Now what are the boundary conditions I use? E4 of what is the boundary condition on E4? Yes. Because beyond this point there is no medium. So any phase conjugated wave can only develop from this point onwards in the forward direction. So there is no E4 beyond this point. There is a finite E4 here. There is no E4 at, so all the backward wave gets generated at the point less than L. So at L, any wave at L should have come from beyond L, and there is no medium beyond L, and so there is no electric field E4 at L. And of course, E3 of 0, which is the wave which I am sending, say E3 0. E3 0 is the electric field of the incident wave at this plane, and so I can substitute these boundary conditions. So E4 of L is equal to 0 implies A cos mod kappa L plus B sin mod kappa L is equal to 0. This implies A is equal to minus B tan mod kappa L. Okay. Now I substitute this second boundary condition in this equation and use this fact that A is minus B tan kappa L. So I will get E3 star 0 is equal to I mod kappa by kappa. Okay. So Z is equal to 0. So the first term goes off here. So I will simply get B times okay. So this implies B is equal to minus I kappa by mod kappa into E3 0 star. So let me get the final solution for E4 of Z. E4 of Z is equal to, now A is minus B tan mod kappa L. So this implies A is equal to I kappa by mod kappa E3 0 star tan mod kappa L. I have substituted the value of B in this equation to get the value of A in terms of E3 0 star. So let me write E4 of Z is equal to I kappa by mod kappa E3 0 star tan mod kappa L cos mod kappa Z plus, so minus sine. I have substituted the value of A and B here. This I times kappa by mod kappa E30 star is common, and I get a tan mod kappa L in the first term and a minus 1 in the second term because of the minus sign. What I am interested in is what is the value of E4 at this point, because beyond this, once E4 comes out, it's just going to propagate backwards. There's no more generation of E4 or modification of E4. So what is I'm interested in is E4 of 0. E4 of 0 is equal to I kappa by mod kappa E3 0 star no, z is equal to 0. So that is 0. So this is the, so suppose I were to interpret this as a mirror, how will I define the reflection coefficient? E3 0 is incident and E4 0 is coming out. So the reflection coefficient, the energy reflection coefficient of this mirror would be R is equal to mod of E4 0 by E3 0 mod square, which is equal to so if tan kappa is more than pi by 4, this is more than 1.
We had the approximation.
What approximation?
So it can be greater than 1.
Yeah, I have not put any approximation on mod kappa L. I have only put an approximation that E1 and E2 are count. I am not differentiating E1 and E2 with respect to Z. That is no pump depletion. First thing is, you notice that if mod kappa L is more than pi by 4, the reflection coefficient is more than 1. So it's an amplifying mirror. It reflects, phase conjugates, and amplifies. Okay, so it's a very interesting mirror because it amplifies. And secondly, what happens is, if mod kappa L is equal to pi by 2, this becomes infinite. What does it mean? You can get a reflected signal without putting an input signal. This is the condition for oscillation. This medium starts to oscillate. It starts to generate wave on its own, because even if there is a slightest noise which enters as E3, because the reflection coefficient is very high, as mod kappa L tends to 1, tends to pi by 2, because the reflection coefficient is very high, the forward going wave, which is a very, very small wave, generates a very strong backward wave, which then actually also generates a strong forward wave, because we have not looked at the second solution yet. So what's going to happen is, as mod kappa L tends to pi by 2, this medium starts to resonate and starts to generate waves. Now these waves are obviously coming from those two waves. The energy that is generated here is from these two waves. Okay, now let me look at the other solution, E3 of Z. So I am interested in 3 of L, which is what is coming out. So E3 star of L okay, E3 star of L is actually I mod kappa by kappa into minus A. So minus A is, let me substitute from here, minus I kappa by mod kappa E3 0 star tan mod kappa L into sine mod kappa L plus B, which is minus I kappa by mod kappa E3 0 star into cos mod kappa L. I am just substituting into this equation, which is the expression for E3 star of Z, the values of A and B, which we have found out, and at Z is equal to L. That's a transmission coefficient. The mirror is the region between Z is equal to 0 and L. So wave is incident from here, It generates a wave in this direction here, reflection coefficient and the transmission coefficient here. So let me simplify this. So this mod kappa by kappa cancels off. With the minus I coming out, that becomes plus 1. So E30 star tan kappa L, sin kappa L plus cos kappa L is one by cos mod kappa L. Okay, because you have tan is sine by cos, so sine square plus cos square by cos kappa L, and that is simply E30 star by cos mod kappa L. And E3 at the output is always bigger than E3 at the input. It's an amplifier. It's like a parametric amplifier. The energy for this is coming from the two pump waves, which are E1 and E2. So what is actually happening is this E1 and E2 waves are mixing together with the E3 wave, and the generating waves correspond to E3 and E4. And so every time you generate an E3 and E4, please remember all of them have same frequencies. So one photon at omega E1 from this wave, one photon from here will dissipate and generate one photon here and one photon here. So this is a very interesting mirror. It's a very interesting device which is called a phase conjugator, and if you satisfy certain conditions, you can actually make it resonate. It becomes an oscillator. Because if you satisfy mod kappa L of the order of pi by 2, then you can have this medium generating waves in two directions. Okay. So this is one interesting aspect of three-way mixing, the four-way mixing that we have been discussing. And this has applications in many areas, like as I was mentioning yesterday in correcting distortions of waves as they pass through distorting media. Because this one is a phase conjugating wave medium. So as I mentioned to you, what I've done here in the class is essentially showing that a plane wave incident generates a phase conjugated plane wave. But please note that any wave can be written as a superposition of plane waves propagating in different directions. So this phase conjugate mirror will phase conjugate each one of the plane waves. And you can show that for an arbitrary input field into this medium, you will exactly generate the phase conjugated wave of that wave, irrespective of what the wave is. So if it's a diverging spherical wave, it hits and becomes a converging spherical wave. A diverging spherical wave is, how do I write an expression for diverging spherical wave? Exponential I k r minus omega t by r. So this will become exponential I minus k r minus omega t by r. A diverging spherical wave becomes a converging spherical wave. So if you had this medium like this, and if you had a wave coming here, it reflects and comes back to the same point, irrespective of where it is. So you can actually use this to compensate for distortions. If you had a distortion here, what will happen is, if there was a distorting medium in between, in the forward direction the wave gets distorted. Because the phase conjugate comes back, that distortion exactly gets cancelled by propagating through the medium again. If it was a normal mirror, the distortion will add. This is a phase conjugate mirror. So because it is a phase conjugated wave returning, the distortion in the forward direction gets cancelled by the reverse propagation direction. So what you get back here is exactly the point source, point image again. The entire wave focuses here. If it was a normal mirror, you would have got double the distortion. So, well, I'm not discussing more details of this, but there are very interesting applications of this, and there are different methods to produce phase conjugation, and what I've shown here is how to use chi3 in a medium to generate a phase conjugate situation. Okay, so with that we complete the discussion on classical aspects of nonlinear optics. So we have essentially seen second harmonic generation, we have seen parametric down conversion, parametric amplification, parametric oscillation, And with the chi3 effects, we started to look at cell-phase modulation, cross-phase modulation, four-way mixing, and so on. So in the four-way mixing, we didn't discuss too much, but this gives you a flavor of the effects of nonlinearity generated by the chi3 in the medium. So next, what I would like to do is to get into the quantum aspects of light. So what we will do is first we will look at quantizing the electromagnetic field and studying some of the properties of the quantum nature of light. So the question arises, why should I quantize light? As we have already seen, for example, parametric down conversion, classical picture does not predict the existence of this. Classical picture does not allow you to generate spontaneous emission. And plus there are many other experiments which people started to do some time back which have no classical explanation. So there is what is called as a semi-classical theory where you treat material as quantized, atoms as quantized, but light as a classical field. It's called semi-classical. A full quantum theory implies that your media are quantized, the atoms are quantized, and light is also quantized. So this complete quantum mechanical picture explains all experimentally observed results. And so when you do an experiment, whatever results you are getting from that experiment are explainable from the picture of complete quantization. So there are, wherever semi-classical analysis predicts different results, it is the quantum theory which is the correct result. In most situations, maybe semi-classical and quantum predict very similar results. So that's fine. But then if I need to get a correct interpretation, I need to use the quantum nature of light, which is essentially I need to quantize light. Now, before we start to look at the quantization of electromagnetic field, let's start looking at some simple experiment. So I have, for example, I take a beam splitter. Okay, this is a device in which you send light from here. It partly transmits and partly reflects. So depending on the transmission coefficient and reflection coefficient, you can have 50%, 70%, 30%, etc., etc. So let me take a 50% beam splitter. So if I send in 1 milliwatt of light here, if I assume there is no absorption, there is no other effect, I will have half a milliwatt coming here and half a milliwatt going here. Now I continue to reduce the intensity of this light. Okay, so I come to a situation where the intensity has become so small that there are single photons coming now. I still don't know what the photon is, but let me assume that the intensity has gone so low. And in fact, there are now sources available which send single photons. That means the energy is h cross omega. Okay, so what will happen if I start to send single photons from here? So if I have a detector here and a detector here, so 50% of them will get reflected and 50% of them will get transmitted. This beam splitter cannot split the photon. The photon is either reflected or transmitted. I have no way of predicting whether the next photon is going to be transmitted or reflected. So if I try to correlate the measurements here, they'll be completely anti-correlated, which means whenever either this will detect or this will detect or this will detect or this will detect. So the simple picture that I get is either the photon gets reflected or the photon gets transmitted. I want to see whether this is the right picture. So I don't stop the experiment here. I continue and put two mirrors and bring them back into another beam splitter. What is this? An interferometer. So normally, classically, light waves come from here. They split into two parts, go through different arms, come back, and depending on the path difference between this and this arm, you will have constructive and destructive interference. So if the arrangement is completely symmetric, you can ensure that light coming from here only comes out from here. If the path difference is exactly 0 among both arms, you see this light goes transmitted, reflected, this is reflected and transmitted. They are identical paths. If all elements are identical, they will be in phase here. This wave is transmitted and transmitted. This wave is reflected and reflected. So they are different. One is going through 2 transmissions, the other is going through 2 reflections. While in this arm, transmission, reflection, reflection, transmission. Assuming that these 2 beam splitters are identical, I expect all the light to come from here. Now I send single photons. I still see them coming here. If my earlier picture, that light when it arrived here, either goes here or here is true, I should have got some photons here. Because the photons could have 50% chance of coming here, then out of that 50%, another 50% of going here, so 25%. But there's also a 50% chance of coming like this and a 25%, so make it 50%, 50%. But I never observed this. I never see a photon coming here. All the photons arrive only here. So it looks as if the photon is taking both the paths. If there is to be interference, there is no way other than that the photon, in a classical way, I will say the photon is going through both arms. If I were to put a detector here, I will always see a full photon or no photon. If I remove this detector here, the photon always arrives here. So it looks as if the photon is actually sensing both arms. It is at both places simultaneously. So the picture of a particle which is going here and there is not a very correct picture for photons. So somebody said, okay, maybe the photon knows that this interferometer is there, so it will take both paths, and if it knows you are putting a detector, it will go through one of the paths. So people said, I'll beat this argument. So what the people did is, they decided, suppose I remove this beam splitter, what will happen? It is exactly this experiment. If I remove this beam splitter, there is no interference. There is reflection, there is transmission here, and there is reflection. So all I have done is to flip the 2 arms, that's all. So what I do is, I allow the photon to come. After it has crossed this beam splitter, I decide to insert the beam splitter or do not insert the beam splitter, to fool the photon. I still get the same experiment. I still find if the beam splitter is there, irrespective of when you have put, all the photons arrive here. If there was no beam splitter, there are 50% chance of getting both the photons here and here. Interference is a purely classical phenomenon, while this is a purely particle phenomenon. I need a theory which can explain both results. See, my analysis, my mathematical theory should explain this as well as this. And that quantum mechanics does. The quantum theory of radiation, when I quantize the electromagnetic field and introduce the concept of photons, I will find that all these experiments are explainable. The problem is conceptually understanding what exactly is happening in the system. So there are a large number of experiments in which they have measured and found that there is complete anti-correlation between these 2 detectors. And in this experiment, as you change, for example, the phase of one of the arms, you can change the interference here, which is standard classical experiment. But the problem is, when I start to think of single photons, then changing this, if it had occupied one of the arms, then changing should not have so much effect. But there is interference taking place in the setup, and the quantum mechanical analysis will predict all the experimental results. So there are a number of experiments. This is just a sample which I explained to you here, which need an explanation in terms of the mathematical analysis, and what I need to do is to quantize Maxwell's equations. Now, you know, in quantum mechanics, we represent the state of a system by a ket vector, and all observables are represented by Hermitian operators. So I would urge you to go back and read a bit of quantum mechanics back again to recall the quantum mechanical principles, because we will use the harmonic oscillator problem here very deeply, because actually I will show you that electromagnetic field can be written as a superposition of harmonic oscillators of various frequencies. So the quantization of electromagnetic field is exactly the same as the quantizing of the harmonic oscillator. And you recall that in a harmonic oscillator, it has discrete energies, h cross omega, n plus half h cross omega. So I get the same kind of a feature here. And that is where I will introduce the concept of photons. So when I have an energy which is n plus half h cross omega, I will say that this field has n photons, because energy is n plus half h cross omega. The level of excitation is corresponding to n photon excitation. Okay, so we'll stop here. We have a quiz now. So in the next class, I will start the quantum mechanical principles, we'll start to quantize the radiation field, and discuss the concept of photons, etc. Okay, this is the classical picture. Here is an interferometer. This is an optical fiber, and the length of this fiber is 1 kilometer. Okay, I'm giving you the area of cross section of the fiber is 100 micron square. Lambda is 1.5 micrometer, and N2 is 3 into 10 to the minus 20 meter square per watt. So when the input powers are low, light comes out from port 1. As I increase the power, I find that at some power level, light comes out from port 2, not port 1. So what is the power that I must input here for the light to switch from 1 to 2? We have discussed the basic physics behind this problem.